This little video is going to take you through the work on Coulomb's law. The law was first stated in 1785. A French physicist by the name of Charles de Coulomb, and the law is used to determine the force of attraction or indeed repulsion between two charged particles. If you have a look at the two orange particles, one positive, one negative, and opposite charges attract, so in that case we would determine a force of attraction. The two blue particles, obviously both positively charged, would be there would be a force of repulsion, and so the law would be used to calculate that force of repulsion between the two particles. Right, the statement of the law is F equals K Q1 Q2 over R squared. Let's go through each symbol. F stands for the force of attraction or repulsion, and as with all forces, is measured in newtons. K is a constant. It's called Coulomb's constant, and it has a value of 9 times 10 to the 9. That value is given in your data sheet, so it's not a number you need to remember, and make sure that you write it down correctly from your data sheet. Q1 and Q2 refer to the charges of the two particles, and charge is measured in coulombs. And R is the distance between the centers of the two charges, and that's measured in meters. Now be careful here. Often the charges Q are given in nano or micro coulombs, because a whole coulomb is actually a very large amount of charge, and the distance again often given in millimeters or centimeters, and you need to be careful to change them to the correct units to ensure that your force comes out in newtons. A couple of things to note about this particular formula. Firstly, note that the force is proportional to the product of the two charges. Now, we're talking about a scalar product here, so we're interested just in the magnitude of the charges, not whether they're positive or negative charges. Positive charge would be indicated with a plus sign, negative with a minus sign, but when we're doing this calculation, we're not interested in those signs. You just need to determine at the end whether it's repulsion or attraction. So that's the first thing to note. The second is that the force is inversely proportional to the distance between the particles squared. And that's something that we call an inverse square law, and you'll come across them in a couple of different situations. You might remember from Newton's universal law of gravitation, that also is an inverse square law, and you can see that that formula looks very similar to the formula that we've just looked at in terms of Coulomb's law. But it's important to note from this that as the charges increase, you have bigger charges, the force of attraction or repulsion increases, and as the distance between the charges increases, they get further away from each other, obviously the force decreases, but it decreases by the square of the distance. And so the force rapidly deteriorates or decreases as charges move away from each other. All right, let's look at a statement of Coulomb's law. Obviously, you need to learn this one off by heart and be able to push it out when required. It really is just a statement of the mathematical law, F equals K Q1 Q2 over R squared, and it reads as follows. The electrostatic force between any 2 point charges is directly proportional to the magnitude of the product of the charges, that's Q1 times Q2, and inversely proportional to the square of the distance between them, that's the divided by R squared. Okay, let's try some common problems. We'll do two simple ones. Firstly, looking at the calculation to determine what the force is between these 2 point charges, P and T. You can see P has a positive charge and T has a negative charge. Both of them are times 10 to the minus 9, which is a nano coulomb. And let's imagine that the distance between those two charges is 30 centimeters. So the formula we're going to use is our Coulomb's law formula. F is K Q1 Q2 over R squared. K is 9 times 10 to the 9 from your data book. Make sure that you get that in correctly and don't make a mistake. Q1 is 3 times 10 to the minus 9. Notice we've left out, in this case it's a positive sign, but we're ignoring the sign because this is a scalar multiplication that we're interested in. Q2, 6 times 10 to the minus 9, that's the value of charge on sphere T, and again notice that we haven't included the minus sign. And we divide that by r squared. The distance between their centers is 30 centimeters, so that's 0.3 meters. Notice I've changed that, and don't forget to square it. And if you work that out, it gives you a force of 1.8 times 10 to the minus 6 newtons, and we can see that that's a force of attraction because we have a positive charge, that's P, and a negative charge, T, so opposite charges would attract. The second problem is commonly asked as a multiple choice problem, and what we would call a ratio problem. So let's have a look. Two identical small metal spheres on insulated stands carry equal charges and are a distance d apart. Each sphere experiences an electrostatic force of magnitude F. They are now placed a distance of a half d apart. And the question then asks you what's the new electrostatic force. So all that's happened, we've kept the same charges, we've just brought them closer. And in fact, we've halved the distance between them. All right, let's see how we'd go about this. This is the original situation where we've got our two charges. Remember, they're equal, so I've indicated them with both Q, and they're a distance d apart. And we're told that the force has a value of F. The charges are then brought closer together, and the distance is now a half d, and the question's wanting to know what the force is. So we would use Coulomb's law. F is k q1 q2 over r squared. I think we can immediately discount option A and B. Because we've brought them closer together, the force must be greater. And A and B shows half F and F, so it's definitely going to change, and it's certainly not going to get smaller. So we can discount those two. The initial force is given by k q1 q2 over r squared. Now k is a constant, so we leave it in there. q1 and q2, I've just indicated them as small q's, and so when you multiply those two together, you get q squared, and the distance between them, r, is given by d. So our initial force can be given by k q squared over d squared. The new force that I've called F2, again, k is a constant, that stays the same. Q remains constant because we haven't changed the charge, but we've now halved the distance. So it's a half d all squared. And if you square that out, if you square a half, you get a quarter. If you square d, you get d squared. So that becomes a quarter d squared. And if you pull that out, it's then 4. If you take the quarter up to the top, it's 4. And then what's left is kq squared over d squared. And you'll notice that F1 is kq squared over d squared. So F2 is equal to 4 times F1. And so the correct answer there is D. Now, I'm going to re-look at this question and show you another way of doing it that some people prefer. It doesn't use straight ratio. What we're going to do is we're going to put in some imaginary numbers. And remember, these are just make-up numbers, but it does help us to work out what happens to the force. So it looks something like this. Let's imagine that those two equal charges each have a charge of 2 coulombs. I've just made that number up for the sake of this problem. A distance d apart, now again, let's just make up a number for that, and I'm going to choose the distance to be 2 meters apart. And obviously when that distance is halved, a half d thus is 1 meter apart. Okay, so our initial force, we're calling F1, is k q1 q2 over r squared. Now, again, I'm going to make up a number for k. It's not 1, but as long as I use the same number for both, I'm all right. So I'm just making up a value for k, calling it 1. q1 and q2 are both 2, and the distance r is 2. So it's 2 times 2 on the top, divided by 2 squared on the bottom, which obviously just gives us 1 Newton. Now, that's not an actual calculation of real numbers, they're just made up numbers, but all we're going to do is compare that to now what happens for F2. So F2 again is given by Coulomb's law. K, I've made 1 and I'm using it as the same value as I did for F1. Q1 and Q2 have stayed the same, so they're both 2. But R now is only 1 meter, and so it's 1 squared. And so it's 2 times 2 over 1 squared, which gives us an answer of 4 newtons. And now you can easily see that F2 is 4 times the value of F1, and the answer then is D. So that's another way of approaching these kind of questions. that you might like.